everyone. I'm Liz Stewart from Department of Mental Health and the Bloomberg American Health Initiative. Happy to have you all here and anyone who's listening online, especially given snow and possible school closing. So thanks to those of you who made it here in person. This is the last of a 4-part series of seminars we've had sponsored by the Evidence Work Group of the Bloomberg American Health Initiative. This previous topics included data resources for opioids research, educational and childhood data in Baltimore, and spatial data, and those should all be available online at some point. We recorded them all, so you can go back and watch those. I also just wanted to give a quick flag that actually today's an exciting day for the initiative. So those of you who want to learn more about the Bloomberg American Health Initiative and sort of the role of public health in improving the health across the US, there's a brand new supplement of public health reports that literally came out today with articles on each of the 5 main focus areas of the initiative, and then 3 cross-cutting topics: equity, evidence, focus today, and policy. So you can read that supplement. I believe it's available for free online, and that gives you a really nice overview of the initiative and some of the areas for work. So just wanted to flag that given the timing today. So I'm really happy today to have Nilanjan Chatterjee here to talk to us about large-scale cohort studies and their role in studying public health. Dr. Chatterjee is the Bloomberg Distinguished Professor with appointments in biostatistics and the School of Medicine. Before he came to Hopkins, which was a couple years ago, he spent a long time at the National Cancer Institute, and before that got his PhD from the University of Washington. He's one of those people that if I read his accomplishments and awards and things, it would take a really long time, but he's also just a really generous, great person who has done a lot of really good thinking about how to really best leverage data for public health purposes, whether that's prediction models and also really innovative methods for combining different data sources, which I think is really relevant for a lot of what we do. So really happy to have him here. He'll give a seminar and then we'll have some time for questions at the end. Thank you.
So how long should I speak?
One-ish.
Okay. Thank you, Liz, for organizing this, and it's a real pleasure. And the greatest pleasure I had because of that talk I have to give, I have to learn a lot more about UK Biobank than I knew, and that's, I think, that pushed me. We have been using some of the resources, but but we really didn't follow everything, starting from study designs and how the data was collected. So I think we have a little bit more knowledge about these amazing data sources as well as other biobanks. So really great to share this with all of you. Like, it's a real, I think, literally gold mine for anybody who is doing in public health, chronic disease epidemiologic studies. Cannot believe that this kind of data are actually freely available and will become more freely available in the future. I want to really start with an acknowledgement, because this is not, as you can believe that working with the UK Biobank data, exciting, but it is not an easy task because it's a huge amount of data, complicated application process. But even after you get the approval of the data, there are a lot of data management, data wrangling, data access issues. And I could not have done with this without Prosenjit Kundu, who is a PhD student who is working from early on from my application when I was working in the UK Biobank. So he was really instrumental to actually, once we got the approval, to download the data, store it, manage it, and actually put it in a format that is we can start doing analysis. We are actually now, this is the year we are doing analysis. And also more recently, 2 other members of the biostatistics department, John Mushali and Andrew Leroux, they have joined, and especially they are very interested in working with the accelerometer data because of their interest in that, and they have been also very instrumental to move this forward. So I think, I because I was trained in epidemiology, the biostatistics, but a lot of strong connection in epidemiology, and I think we all know that cohort studies is the bedrocks of doing chronic disease epidemiology, and it has been historically so over a long time. And those of you know the famous British physician study that basically established that smoking is a risk factor for coronary heart disease. That was in 1951. And since then, cohort studies has emerged, because you have heard some of the very famous cohort studies like Framingham heart studies, our own EDIC study, Seattle's Freda Chinchen's Women's Health Initiative, Nurses Health Study at NCI. I worked a lot on this study called prostate, lung, colorectal, and ovarian cancer screening trial, but that can be used as a cohort study as well. But what I started noticing is that in the beginning of this millennium, around 2000 onwards, for some reason, I don't know whether it's a coincidence that the century turned, there was suddenly a push towards really scaling up this effort of these cohort studies, and not only in terms of sample size. So, like the sample size of the other previous cohorts were range from 10,000 to 100,000. The one that are biggest would have a little bit more than 100,000. But the push was to make it much bigger, to the hundreds of thousands to even millions. But not only in sample size, to make it much more richer in terms of the available exposure information by exploiting all kind of new technologies that are becoming constantly available. But also in terms of much richer phenotype information by taking advantage of electronic medical records, to link it with various kind of outcomes. So that's what in my mind is mega-cohort is nothing but a cohort, but in a much more scaled, both in terms of both sample size and the type of information that is available. And so one of the first time I got interested, because we know that why do we need suddenly big cohort studies? Forget the technology part is of course very interesting, but why do we suddenly need to increase the sample size? And I remember 2006 or 7 by happenstance, I was in a presentation where one of the key PI of UK Biobank was making a presentation when they were just starting the study to make the point, that what big sample size can do. Although statisticians, we know that with big sample size, standard error gets smaller, but until you see it, what it does actually in reality, you don't really understand the importance of it. And to make that point, I really like the slide, very simple. So this is showing the association between standard blood pressure and coronary heart disease rate, and that you can get from, let's say, 5,000 people. They have sampled from UK Biobank only 5,000 people, and they are trying to see the association between getting increased blood pressure and the heart rate. And you do see there's an overall trend increasing, and they have stratifying this by age, but because of the large confidence interval, it's really hard to distinguish whether there are different patterns there. But you see an overall fuzzy picture. Now they said, okay, let's do it based on the 50,000 people, the same hypothesis, and now you start seeing that the patterns is becoming more clear, especially the age-specific pattern. They are stratifying by age, and then they're showing how the relationship between blood pressure and heart disease changes. And then you do it based on 500,000 people, and then become really clear. Again, statistically, it makes all sense, right? Because the standard error is going down and down. But actually, if you're seeing it, it sort of says, oh, yeah, that's really interesting, right? Especially if I really want to, these kind of studies are being long been used to decide guideline for blood pressure, what is the optimal blood pressure you should maintain, so that you don't get over treatment, and that is really changes by age. You really want more precise estimates. So so that I think you can see even a very simple question is not a there's a well-known risk factor for heart disease is the blood pressure. Understanding risk, especially in subgroups, what is the power of the big sample size studies. Another one, that is I work on a lot is the genomic association studies, where there is for example, I'm going to take some figure from a recent paper we published, where we are using current genomic association studies for, let's say, 3 diseases: one psychiatric disease, autism; one is autoimmune disease, Crohn's disease; another is a adult onset, very common disease, type 2 diabetes. And this paper was about understanding, using the current data set to understand what is the genetic architecture of these different disease. Based on we did some modeling, and we found that each of the disease is related to many genetic variants. And these are the number of genetic variants that are associated, we estimate. There are thousands of them, sometimes there are tens of thousands. And this is showing the distribution of their effects and of those thousands of variants in terms of log odds ratio. And the main point to show that there are thousands of them, but each variant has very small effects, because the log odds ratios are all between 0.04 to minus 0.04, 4% increase in risk is sort of the maximum. There are many more much smaller effects. And this side is showing that how big sample size we'll need in hundreds of thousands. This is in 1,000, so 100 means 100,000, how big studies has to be. Cases we need to discover those variants, identify those. I can estimate how many are there, but I have not found which are the variants. And this shows that how big studies we need to do to actually identify those variants so that I can put, for example, in genetic risk prediction model or polygenic risk score or understand biology. And so you can see like, that we will not reach the plateau for these kind of diseases until we have hundreds of thousands of cases, or even sometimes for psychiatric disease, which are more complicated, you may need even 500,000 or 1 million cases, depending on what disease we are looking at. So that's the power of, again, another example that why do we need these super big size data sets, for the next generation of epidemiologic studies. Another one, that is those who have probably seen this, that this technique called Mendelian randomization is revolutionizing epidemiology, modern epidemiology. It's a very simple idea, like we know that big data is not the solution, right? Big data, you can do epidemiologic studies, you can have big data, but this is still observational studies. So you will find association, but you do not know that whether this association means causality. So another field has emerged, to sort of, from this big data approach, is this called Mendelian randomization approach, which is like a primer on Mendelian randomization, how it works. If you think about what is the gold standard for establishing causality is a randomized trial. Suppose you're trying to show that LDL is causally related with heart disease risk. So what you might do that you may design a clinical trial, and then you randomly assign with a LDL lowering drug, and then one is the treatment arm and the care arm, and then you see among those two randomized group what is the event rate. And if there is an event rate difference, then you can say that yes, this is a causal, LDL must be causally related, because there is no other way these differences would happen because of the randomization. So, but we cannot do this for clinical trials are very expensive, and so this LDL, HDL both are known to be associated with as a risk factor for heart disease, but we do not know that whether these associations are causal, and that's a very important question, because then although we know they are risk factors, but which should I target if I want to reduce my heart disease risk? That's a different question. So the idea is that you can use genetic variants, suppose we find the genetic variants which is associated with LDL, and the genetic variants which we inherited, it is sort of randomized, because we get the alleles, which allele we get from our parents, that's sort of randomly determined. It is not confounded by other epidemiologic factors, like that the other lifestyle factors. So you can think about that genotype we get from our parent is a random assignment. Somebody will get the risk genotype and somebody will get the lower genotype, and that assignment is random. And so basically think of that random genotyping assignment is sort of acting as a treatment assignment. And then if you have some people have some genotype, they will have elevated a lower LDL level, and the other one will have normal LDL level. And then if you can show that these two group has a different heart disease rate, then under the some assumption, this genotype has no other way of affecting the heart disease rate, that does not go through the LDL path, that shows some evidence of causality of the LDL on a heart disease risk. And so this was an idea, it was proposed around 2000, and I was a disbeliever, because for simple reason is that conceptually it works, but the problem was that I thought that the effects, that the effect of the genetic variants to the biomarker is very weak. And so now I want to look at the effect of the genetic variants on the outcome is going to be even weaker, right? So I need huge sample size, and I said that it's never going to be possible, to do this kind of studies, to this kind of Mendelian randomization studies, simple because these are so weak effects. But because the sample size is no more the limitation for at least for genetic studies, it is has become a very fundamental tool in modern epidemiology. I will see nowadays the field is like flooded with including big journals about all kind of Mendelian randomization studies, but those are becoming possible because of these large biobanks, which can link your genotype data to exposure data, biomarker data, electronic medical record data, and to test for causality between various type of biomarkers and various type of disease outcomes by using these large data sets. So that's another, I would say, great advantage of having a large data set for studying causality. So one of the biggest and most successful biobank, that is going to be the main theme of today's lecture, is the UK Biobank, which is and this is a more advanced biobank, and they started in the UK Advanced. They started thinking about this around 2004 and 5, and that's why they actually have a lot of data, and these data are publicly available in the sense that you do have to go through an application process, but everybody can potentially access this data. And this has been I think, a phenomena in the biomedical science. This is probably now considered the largest and the best available data that has ever been generated. And that evidence of it, you can see that already, although the follow-up time is only, I would say, 10 years, but still it is generating amazing amount of discoveries. I'll just give you some examples of recent publications. You can see from genetics to air pollution to imaging to eye disease, all kind of purpose people are using these data sets. And there are major publications coming out, and these are just some of the word clouds. You can see everything you can imagine about population health, public health. They're studying using these data sets. And then US is also playing catch up with their, that is, I think they realize after that, oh, UK Biobank is launching and other countries are launching these big mega cohorts, and they realize that US, they also have to do something like that, and that is going to be publicly available. So NIH started this called Precision Medicine Initiative. Now they call it the All of Us Initiative. But the whole purpose is that, they said we will launch a big cohort studies, even bigger than UK Biobank, almost 1 million people now. So that's what we can do. We are a little behind, but we can make the sample size larger. And then it will help to, sort of push the precision medicine, particular precision prevention effort, because if you understand risk factors for epidemiologic studies, we understand causal factors, then maybe we can develop more targeted approach to prevention using these data sets. So let me, I'll go the next slide, set of slides. I'll quickly go over, just to give you some introduction of this UK Biobank, so that you have some idea, and then if you're interested in more, you can talk to us, about, but I must say that I do not know about, I did not design this study, okay? So don't blame me. If you say, why is this participation rate is so low? What about the selection bias? I'm just going to describe you what they have as much as I know. It's a good time because, of course, UK Biobank people who are using it, they know it for a long time, but if you may have seen, in last month, UK Biobank was in the Nature cover because of their first couple of publications on the imaging data and the genetics data. That was and they described in this paper that, and the first results from the genotyping data. But this is a good paper to read if you do not know about UK Biobank, that's a good overview. So it's a cohort study in a sense, about 500,000 people, about 42, they aged 40 to 69, and the recruitment happened during 2006 to 10. And they collect data of using all kind of modalities, which we'll talk about a little bit more detail in the next set of slides. So some basic study design. This was nicely spread over UK and Wales and England, Wales and Scotland, and they did try to recruit diverse population, urban and rural, with different ethnicity. But for ease of recruitment, the way they recruited was they defined a perimeter around the assessment center, and then they invited people to come. So they identified individuals from the National Health Service records. As you know, UK has very good information, the databases to do that. And they invited 9 million people and about 5% participation, and that led to 500,000 cohort. So as you can imagine, this is not going to be representative. When you have 5% people participating, that will be highly selected. It will probably healthier, and I think there is evidence. People look at risk factors and things like that. They seems like more healthier population than the general population. But as we know that all cohort studies are selected, but they could be still very useful for internal. They're internally consistent. So whatever we can learn, we can try to take it later on for other studies. So this is sort of the timeline. What happened? Between 2006 to 10, all the recruitment happened. At that time, the recruitment, they collected various questionnaire-based information on lifestyle factors and other factors. I'll go into the detail a little bit. They did a verbal interview also with the help of a nurse, I believe. And then there was physical measurements taken. And they took biological samples, blood sample, urine, and saliva sample. And then, since then, there have been a lot of follow-ups to collect more detailed information in a longitudinal way. Various components. So for example, in 2011, the online follow-up was sent for a web-based questionnaire for 24-hour diet recall. Again, they send some people that they send, they email them about participation. Only a fraction of the people participate, and in this follow-up questionnaire. So, for example, in this component, there are about 176,000 people who participated in that online follow-up. And then let's see, 2012 there was a repeat of that follow-up. Is that correct? That it is the same repeat of that online follow-up. Okay. So they did, so they're trying to repeat of those some of the 24-hour recalls over time, and they have started their participation. In 2013 to 16, they actually had an interesting component where they added the accelerometer component, and and they were able to recruit 100,000 people who is going to read this wristband, and from which you can get objectively measured physical activity data, which is very important. As you know, that physical activity is very problematic. A lot of measurement error when you ask through questionnaire, but this would be at least more objectively measured cohort. And it is, although it's only 1/5 of the cohort, but it's on 100,000 people. So that is again amazing large data set. And then on the again there is the imaging visit subsequently. Again, they are trying to collect MRI data on abdominal, brain, heart on 100,000 people. So this is again massive data sets on imaging data set that they're collecting. And there has been further follow-up to collect more occupational history data, and there's more than 100,000 people. And there is a web-based mental health question. I think there are a lot of mental health department people here. So they'll be very excited about that. They got information on about 340,000 people to fill out a web-based mental health questionnaire. And I think that data has recently released even. That that if I'm not correct, if I remember, that there was an announcement that mental health information has been released. And there are digestive health questionnaire. I think that has been already done. And then there will be more questionnaires, sending follow-up question on pain. And that is very, I think it could be related to American Health Initiative, some of the things we are thinking about. And there would be more follow-up plans. Okay, so I'm going to go quickly through some of the details about these different modes, like what kind of information they collected at each stage. So this is sort of all the different type of information that was collected at the assessment center at the beginning of the study. So the touchscreen questionnaire was used to collect information on various basic factors, and these are the different type of factors they got: socio-demographics, lifestyle, environment, standard epidemiologic stuff you get, but also they had psychosocial aspect of their lifestyle, social support, mental health. More touchscreen questionnaire. They had early life factors, which I think is very important. That we know that are very important for many late onset diseases. The early life factors, they have that. Family history, detailed family history of various diseases, and personal health and medical history on very detailed information on all kind of diseases, eyesight, medication, operations, screening, pain. So they are. This is not an exhaustive list, but I'm trying to give you an example of what they have, and also sex-specific factors. These are some of the physical measures they collected. Standard stuff, blood measure, like the eye measures, anthropometric measures, but they have other things, ECG and catheter ultrasound, arterial stiffness, pretty detailed, right, for epidemiologic study, and that all of that information is actually already available. Cognitive functions, they collected data on this kind of things. Some of the things I even do not know. If somebody can explain what is trail making. Anybody knows? Or did I get a typo there?
No, it's
something.
Mental health now.
Okay. I thought you were in mental health. Anyway, so you can see there are things, they are very amazing amount of information they have. They have a lot of detailed information has been collected on these people. And these are some of the imaging modalities, the data they have: abdominal MRI, brain MRI, heart MRI, and this DX assessment, which I do not know. I don't work on imaging, so but they have all this data. And then these are the biological samples. They have blood, saliva, and urine. And then based on the blood, already they are doing assays. They have done blood counts, all kind of blood biochemistry, infectious disease. Of course, we've done genotyping and sequencing that we'll talk about. But these are some of the blood biochemistry data. They are going to make it available. So exciting! You can see there are so many different biomarkers will be available on 500,000 people. They have standard stuff like cholesterols and things like that, but they have inflammation biomarker, immune biomarker, growth factor hormones, all kind of stuff is going to be available. So again, amazing resource for example, doing Mendelian randomization, right? You want to understand whether some of these biomarkers have the causal mediator of your outcome, and you need huge sample size data of this biomarker linked with the genotyping data. So these data sets actually are not available yet, but they are releasing it. That as they are doing the assays, you get releases, and then you can request if it fits into your project. So on the genomic side, that's they have again basically have the genotype data on whole 500,000 people. They also provide imputed data, HLA typing. You get information on the sample quality, population structure, all the detailed processing they did. You can get that data. So you'll be able to work with that data level. And they are going to in the future they're moving towards more sequencing from exome to whole genome sequencing on the entire 500,000 people. So we are working with the genotype data, so we have more experience on that. So they have 500,000 subjects who are genotyped on this UK Biobank exome array, and these were specialized design array where they had a GWAS backbone of about 600,000 SNPs that sort of covered the whole genome, and then people proposed like another 200,000 variants. 100,000 are coding variant, another 100,000 was probably proposed from the previous GWAS analysis, which looks like promising genetic variants for different disease. And this is a custom array they designed so that they have good coverage for those high priority variants. And they have actually now not only that you get the genotype data, but you get the imputed data. So the genotype data on 800,000 people, but you get imputed data almost on 90 million genetic variants. And so the imputation was done based on the haplotype reference consortium, which is about sample size of 60,000 people. So they can actually impute based on the common variants haplotype, fairly rare genetic variants in these studies. So and you get all the data when you request the genotype data, and so it could be pretty large. So I'm going to skip. These are some online follow-up questions I talked about, and these are some additional exposure. You can get actually some of the environmental data, local environment, air pollution, noise pollution. That data is there. Accelerometer data I talked about. So this is, you can see like how rich the exposure information. Okay. So now it is a cohort study. I need to figure out how to get the outcome information, especially the incidence outcome. That means how do I find that who has a new breast cancer or new heart disease and things like that. So the next few slides is about that. So this is a passive follow-up cohort because you are basically linking electronic medical record instead of actually actively following up these people to ascertain the outcome information. And there are different type of data you can do that. One is this is hospital episode data. So basically there is a database from which you can find information for any of these people, like their information on if they had admitted to a hospital, you get all the records related to the hospital admission, like what kind of procedure, what kind of disease they were diagnosed with ICD-9, 10 codes, and what kind of operation they had. So it's a complicated database, but you have that. Further, you have death registry to find whether date of death, cause of death. For cancers, it's better data we have because they have cancer registries, so they're linking the cancer registry data to this information, so you can get directly cancer incidence data from the cancer incidence instead of going to the hospital episode. So just not going to go to the detail. So these are some of the information you get from the different registries and different hospital episodes. And these are some future available data. The more biochemical assay data, and there'll be more updated hospital inpatient and death registry data. So of course they are updating, right? Those are registry data. Like they are update, you get the data up to certain time points, and then in 6 months or a year they'll update it again, and you will get another delivery of the data. So you get updated data over time. And so so that's sort of the UK Biobank part of it. So if you are not already overwhelmed with the amount of data that you have, so here are some other more overwhelming data sets, but these are not so easy to access. So that's why I'm going to mention it, but I'm not going to go into too much detail. The Vanderbilt's Biobank, which is one of the, I think, in the university setting, one of the biggest biobank and best biobank available. The Million Veterans Program, which is amazing, I think, biobank, but it is not so easy. You cannot get their data. You have to actually work with somebody who work in that program and do the analysis there. So it is some access, but it is not as open access as a UK Biobank data. And there are other biobank. And all over the world, now there are biobanks are opening up, not only in the US. So you can see there is a biobank in China. The IARC has their own biobank in Finland, Canada, and Qatar. So the biobank effort is really expanding all over the world. But the only problem is that it is not as easy as like the UK Biobank. The All of Us cohort that is the US is launching, it is going to be open. That is the whole model. That is going to be open from the very beginning. But these ones I am not sure, like how open they are. These data sets are. So just to give a little bit about what we are doing and what is our experience has been so far. So we are working with this data set for about 2 years because it took me 1 year to get the approval. And so one of the things is that when I was moving from NCI, so one of my biggest worry was that, oh my God, what am I going to get my data sets? I had this great access to the NCI cohort studies. And so at that time, and then I did, there is this huge data set, which is much bigger than the NCI data sets I had. Let me try, getting access to that data set, okay? Because that seems like amazing. And it is amazing, but it takes time, So it took me 1 year to get through all the process, understand, do the application, and things like that. And then the last 2 years, I think we are basically trying to manage the data, understand what is under the hood, and what we are doing is that, basically. One of the most complicated part is the dealing with the electronic medical record data, the hospital episode data, right? Because it's not I'm trying to define clean survival type of outcome. When did they have the disease? What age? Okay, what is the first time? And that data is not as cleanly as available as in a cohort study. You have to sort of mine that electronic medical record to define your outcome, and that's kind of time-consuming and messy. We are learning as we go, but we are making progress. Of course, we are doing a lot of coding of the covariates and exposure data, like the standard epidemiologic stuff. And then also we have experience in analysis of the massive genotype and the imputed data. So here are some ongoing projects we have that we are actually doing right now. Now that we have, we are being able to develop pipelines for data analysis. One is the validation of cohort studies are great for validation of risk prediction models. That's what we, including genetic, models that include polygenic risk scores. We are doing Mendelian randomization studies. Sort of, taking advantage of all the instruments, the genetic instruments that are emerging from the UK Biobank for various type of, biomarkers and epidemiologic factors, and doing various Mendelian randomization studies. I'll give 2 examples of that, and then recent study we are doing is the taking advantage of the accelerometer measured physical activity data. Now, that one was started later, right, 2013. So the follow-up after 2013 is less. So the number of events we have for these various outcomes is less, but still pretty exciting. Whatever data we have to be related to the overall mortality, cause-specific mortality, the heart disease, to see how much this objectively measured physical activity gives me compared to everything else I have on these people. That's sort of a very exciting study. So just a quick example of, for example, like like one study we did. We're trying to validate a model that we have developed earlier for predicting breast cancer risk using both genetic factors, genetic risk scores, as well as epidemiologic factors based on previous studies. And we are trying to, basically in the cohort, we have about 136,000 women, which are for which we have the genotype data to validate this model and the risk factor data. And this is a model we described earlier in 2016. And like that was one of the first model for predicting breast cancer risk, which incorporated both epidemiologic factors and genetic factors by integrating information from all kinds of studies, epidemiologic studies, genetic studies, disease incidence rate in the population, and risk factor distribution and things. And then we made projections, right? But we did not actually, have data to validate the model. But now we are in the process of how good the, the model is going to validate if we take in another cohort study. So that's sort of, in the UK Biobank. So we are looking at sort of, this is the expected versus observed plot. So we have expected risk based on our model. I can put people into categories, into the people who are low risk to high risk, divided into deciles. And these are the expected risk, absolute risk of developing the disease. And this is the actual proportion of people who develop the disease in those categories. So you see, we have, not bad, but in the highest risk category, it seems like we are over-predicting the absolute risk. The actual risk is slightly lower than the observed risk. But if we look at the relative risk, this is absolute risk. But if we look at the relative risk was pretty well calibrated. It is so I think like the absolute risk is harder, right? Because you have to sort of calibrate it to the population based on their incidence rate and things like that. So it's kind of expected that it will be more challenging, but at least we see that the relative risk part is very well calibrated, and that is really reassuring, right? Then we develop the model with a lot of effort, and now this is a large cohort study, which is, although only about, I think, 7 years of follow-up, they already have 3,000 breast cancer cases, right? That's a large number of cases for a cohort study, because their base is so large. And so this is a massive, fairly large validation study, and that's nice to see that. Another example, quick example of a MR analysis, like just to give a flavor of things we are doing. So, as I said, that the UK Biobank analysis of doing GWAS for various type of exposures, like BMI, cholesterol, other biomarkers. You're finding there are genetic variants which predicts these biomarkers or these epidemiologic factors, right? Now I can use those as an instrument to see, for example, like cholesterol, like LDL. I want to see that is this genetic variance which predicts LDL, does it predict heart disease in a sort of a Mendelian randomization way? And there are issues, but the main thing is that, as I said, the biggest problem is that this genetic variance has very weak effects. So there's very poor power to do the test. But the advantage is that this kind of having these large data set, we have many genetic variants that are emerging from this kind of analysis. So we can take advantage of that to do a more powerful Mendelian randomization analysis. So I'm going to give an example of looking at the known epidemiologic risk factor for heart disease. Okay, these are all standard epidemiologic risk factor: BMI, LDL, HDL, triglyceride, systolic blood pressure, and diastolic blood pressure. So if you do the observational epidemiologic studies, you'll find association of these factors with heart disease. From very large GWAS that has some of them has included, UK Biobank, they have found, for example, for BMI, there's almost 1,000 genetic variants, which is tiny effects, each of them on BMI, okay? But together they explain certain fraction of the, substantial fraction of the variation of BMI. So they all become my genetic instrument for testing the Mendelian randomization. Similarly, LDL, HDL, they would be given even much bigger very soon, and diastolic blood pressure. And then I'm taking all these instruments, multiple instruments, and then I'm running it through various different methods for Mendelian randomization analysis. And there are some methods, like which is sort of say that all of these instruments are valid. That means they cannot have any sort of this called direct effect on the outcome. All the effect has to be through the your biomarker, for example, LDL. But that's a big assumption. So that assumption starts falling apart, because when you are working with so many different instruments, these things has complicated effect. And that's the biggest challenge of Mendelian randomization analysis, that how do you do a proper Mendelian randomization analysis that can account for the fact that yes, there could be some extra effects that is due to the direct effect of the instrument on the outcome that does not go through that biomarker. So this is the method which does not take into account for the possibility that there may be an invalid instrument, and these are some method MR mix which we developed, weighted mode, which are more robust method that takes into account for the invalid instrument. So just a few examples. So BMI, you would think that's a causal factor for heart disease risk, and we do see that that if you do the Mendelian randomization analysis based on this genetic instrument, all of the different methods seem like positively. This is the log odds ratio per standard unit of the increase in BMI, how much your heart disease risk is increasing. All of them seem to suggest increasing. There's a slightly different magnitude, but they are probably not that different. Although, for example, some of the method has very large confidence interval compared to, for example, the other methods. And then if you look at LDL, again, you see that all the methods are suggesting an association, causal association, in the same direction as the epidemiologic association. So that's reassuring, and there's a positive control, because actually the clinical trials have consistently shown the LDL lowering drug actually reduces heart disease risk. So that is consistent with the clinical trial data. But then when you look at HDL, something very interesting is happening. So two of the robust methods, like the MR mix and the weighted mode, which takes advantage of the fact that there are so many instruments, I can actually sort of try to sort it out which are valid and which are non-valid instruments, basically suggests that there is no causal effect. And this is again consistent with the clinical trial data, because when they do the clinical trial for HDL lowering drugs, they don't see consistent association. But if you look at some of the other methods where do not take into account for the possibility that there could be invalid instrument, you start seeing actually the bias that you see in epidemiologic study. They start seeing an association, inverse association that's consistent with the epidemiologic studies. So the point here is that this is all being possible to make this now start investigating these, whether these associations are being potentially causal, and not only looking at known epidemiologic factor, you can do agnostic Mendelian randomization analysis, right? You have so many biomarkers. Some of them we know that has been associated epidemiologically, but some of them we may not even know that they could have potential effects of other outcomes. So you can start doing agnostic Mendelian randomization analysis using the instrument on the biomarkers and all kind of outcomes. And this is all being possible because of this huge biobank data. So I think like this kind of biobank and availability of biobank do represent is a paradigm shift in science. It's basically democratizing science, because in the past like the people who had huge access to these cohort studies, they had an advantage, and not other people had that advantage. But I think that now that you can make anybody with some effort, at least as a group, can make this access the data, is a democratization of science. It's a great thing. And I think in the future, because of the availability of these big cohorts, agencies will fund analysis of data and assessment of new variables, for example, new assays with the biomarkers, instead of starting new studies, because that's what the NIH and the federal agencies are going to do. And the journals will start requiring that if you are proposing some hypothesis, you have your own data, but that same data is available on much larger number of people in a freely available cohort, relatively free. They will ask you that, why didn't you use that data as well? So I think so I think there are opportunities and challenges to handling this data, because these are it requires all our traditional tools for analysis of observational studies, like from understanding study design to bias, cohort analysis, survival and longitudinal data, causal inference. But it's like it's at a more massive scale. So you have to innovate, how to be able to take your standard software or standard method and to scale up for this kind of analysis. And I think like again you need like for both kind of specialists and generalists to analyze this kind of data, because you have a lot of specialized type of data like genetic and genomic data, biomarker data, imaging data, and so you need like those kind of expertise, right? You cannot just go in and analyze those kind of data. But at the same time, you also need generalists, like that who can put all those different type of data together. For example, to ask question, can we develop a risk prediction model using different type of modality of the data? And that's my last slide. As a there's a pitch for the school. I have made it for the department. I'll make it for the school. I think our department or the school actually has been less ready to take advantage of this kind of big mega cohorts. We haven't actually. When I came, everybody else outside was talking about UK Biobank. But when I came to Hopkins, nobody was talking about UK Biobank. So I thought like I should try to make people more aware of. And but this is like takes a more long-term investment, because as I said, paradigm is shifting, and we need to take advantage of that, and we need to be ready to take that opportunity. And so that means we need to make long-term investment from the department and school level to build that infrastructure, because this is not easy. Like even if you think the data is available, accessing the data, managing the data, moving the data, coding the data, it's a lot of effort. And so I think as a group, we should be able to do it together instead of everybody repeating the same thing over and over again. And the whole purpose would be to have an infrastructure so that we can do rapid analysis and publication. We can generate preliminary data for our grant applications, from UK Biobank. Nowadays, people love it. Your reviewers love it if they see that you are actually going to analyze UK Biobank data, whether it's a methodological project or your some AP analysis, and you can generate preliminary data from the UK Biobank studies showing that you have ability to handle that kind of data. And I think it'll be also to have the infrastructure ready will also be helpful for recruiting new people, because everybody wants to analyze this kind of biobank level data. And so if you are sort of pitching a new investigator, you have to show them that you have providing them the infrastructure so that they can handle this kind of biobank level data, and they can quickly come and and bury themselves into that kind of things. And I do think that it also nicely relates to some of the existing initiatives, like the obesity, diet, physical activity part can be easily related to American Health Initiative. The pain data, when they become available, it easily relates to also the American Health Initiative, the opioid part. It is obviously related to individualized health, because I gave some examples of how it is helping to develop and validate a risk prediction model. Obviously related to all data science activities, because it's massive amount of data. So we need all kind of data science tools. So this is like, I think actually this is all, for example, I gave an example. This actually in our group department, we have a lot of working groups, right? And for example, this is already generating collaboration between working groups because I gave an example of working with the wearable technology group, and they are working with the UK Biobank with us. So I think this can help us to bring a lot of initiative and separate groups together. So that's my pitch of using this data for the school. Thank you. Oh, right.
To the webinar can hear them. So just open it up.
Yes.
Hi, thank you for a great talk. My question is related to this last slide about being more ready.
Right.
And specifically, I wanted to ask, when you're going back and forth with these biobanks, what is kind of the timeline that it takes between your initial contact and receiving the data and kind of beginning the process of the design and the analysis?
So the question was, if I get it right, that if you want to access this kind of biobank data, how much time it takes from the initial application or initial expression of interest to actually get data. So I think it varies from the biobank to biobank and your project to project. So UK Biobank, I would say, given the amount of requests they are getting, it is still very efficient. So for me, like the initial contact, pre-application, and to actually receiving the data was about somewhere 8 months probably. But now that process might have gotten slower because I did it earlier. Now there are more and more people applying, and I do not know even how they are managing that process. But the thing is that some of those could be cut back. You can have your project application, say this is what the reason I want to apply. You get the approval, okay? But then when it comes to for example, working with the genotyping data, you can talk to the UK Biobank people. They said, okay, we have another project, right? They have already genotyping data. Can you help me to link? So they do something called institutional access. For example, at NCI, that's what they did. Okay, you still need to have your project approved, because I cannot just give access to as I wish. That's not my data, because my project has been approved under some big umbrella project. But I think some of the data management and data access issues, all the things we went through, not everybody has to go through that, right? Because we have already gone through that. So that's why I think there is a rooms for, that's why I'm pitching that, that we have put all this investment. With some more investment, we can actually make this process much more efficient, that go through the application, and then we can help you to go through the application, and then, and there come the data access and thing. We can work with the UK Biobank people. Yes, please.
Thank you. This was great and very compelling. So playing a little bit of devil's advocate, or sort of actually thinking more strategically about, like, if I was going to NIH to ask for grant funding, I think a common, at least the rumor, is that they would say, well, it's not US data, so, like, why do we care? And so can you talk a little about how you've thought about that and sort of any help in sort of thinking through how do we convince people kind of what parts of this would actually be applicable to? And again, not that we should be US-centric, but sadly, some of our funding mechanisms are. And so just sort of wondering if you have thoughts on that.
Yeah, so the question was that because the UK Biobank data is not US data, whether there would be issue when you do NIH application that this is not US data. So far, I don't have that much experience because I'm relatively new in grant writing experience. But that at least for one methodologic project where UK Biobank was my massive, the main data I was going to analyze. They said like it's very contemporary. They liked it. But I think but more broadly answering the question, first of all, the UK Biobank is a Caucasian sample, right? So a lot of the genetic factors or the etiologic factors, they're not going to be different, okay, between UK and US Caucasian samples, okay? So that's definitely, you can make the argument that, that this is going to be very, very applicable to, now it will not be for the defined ethnic group, like because they don't have Hispanic population, they don't have that many African population, right? So that's where you cannot translate. But, a lot of the biomarkers will find, based on this massive, you can, further take into some validation studies in US-based studies. But you would expect the etiologic factors to be the same. There is no reason to think the etiologic factors will be different.
Yeah, I mean, maybe sort of a comment too. It seems that much of this slide is focused on practical with it, which I think is a real concern, something we should be ready for. I'm wondering too what your thoughts are on
are there ways that we can, or should we be thinking about working together too to understand some of those biases, right, that you alluded to, right, and what is and
Exactly.
not be possible so that we can share it sort of as a
Absolutely. Because
yeah.
so the question was that, we talked about here some of the practical issues, but there are issues in the data analysis, like because this is a cohort study with a very selected population, and there could be potential biases, and whether we can work together to better understand this kind of issues. And I think I absolutely agree that I think like when we started working with the wearable information technology group, that's what we started doing at the beginning. Like for example, the people who are given that accelerometer data, there are 100,000 people, right? So there are 500,000 selected from 9 million people, and there are 100,000 people selected from 500,000 people, right? So there's a lot of selection going on. And I think we don't have to keep rediscovering that, right? So I think we should understand that, we have a little working group currently that who meets on Thursday, to talk about some of these issues. We are welcome, other people to join, so they understand more broadly. But yeah, I think the understanding the selection bias, and then when you do the cohort analysis, who you should exclude, right? And that's a huge issue that I don't think has to be rediscovered every time people are doing. But that's a very good question.
Okay, I'll ask my other question. This is a little bit more in the statistical weeds. Sometimes there's concerns with these huge data sets that statistical significance is hard to think about because you have these, and you sort of alluded to this, like it's tiny effects that are technically significant. So have you thought about that? Maybe it's one of these methods challenges, but you just talk a little bit about how you thought about that.
So from the genetic point of view, actually, because these are tiny effects, but they are real effects. They are not artifacts because there are multiple lines of evidence that they are not artifacts. For example, one line of evidence that you can combine the tiny effects and give the genetic risk score and validate in another population, and you do see that they are showing sort of risk variation. So I think that's more of a reality of the biology than technical artifacts, and that's why you do need large sample size for the genetic effect. But I think my more concern is the epidemiologic factor, where there is going to be a lot of artifacts because of selection, right? Because of confounding, and with these huge sample sizes, they will start looking significant. So that's why I think causal inference has to be very integral part of the big data, because as we know, like I think I like one quote is that big data can give you the wrong answer more precisely, right? And that's exactly what big data is, that you have bias and you have more precision around the bias, so you get your wrong answer more precisely. So I do think that for this kind of cohort studies, like big data setting, you need a causal inference. That's why I'm so excited about the Mendelian randomization aspect of it. But there are other techniques for causal inference, like how to analyze cohort studies in a clinical trial way, like like the kind of stuff Jamie Robbins and Michael Harnan has advocated. All these are applicable here. And I do think that we have more power because those causal inference stuff is although conceptually exists, but they require a lot of power, because you have to do a lot of exclusion and stuff like that. But with the big data, you can do that, right? Because you don't have to, worry about the loss of the power.
All right. Well, thank you very much. This is really informative.
Thank you.